Welcome to the lesson 17 of industrial instrumentation. In this lesson basically we will see that we will solve some problems on the basic temperature sensors like thermistor, thermocouple RT, and like changing in the signal conditioning circuitry. What are the different types of signal conditioning circuitries are there? If they need some particular accuracy, what are the things we have to do? That's all those things we will discuss in details in this particular lesson. Now, contents of this, as I told you, these are problems on the temperature sensor. Contents, the problems and solutions on RTD, thermistor and thermocouple. So, this is the basic things which we will discuss in this particular lesson. So, let us go to the problem number 1. So, this is a problem number 17.1. This is basically on a RTD. You can see one Wheatstone bridge here there. So, this is RTD. You can see this is RTD, and there are some resistors of R, 2R, R and 2R, and this is excitation voltage of this Wheatstone bridge. The question is, determine the sensitivity of the bridge for small value of x, right. If I go back, you can see what is x. So, this is our x. So, determine the sensitivity for small value of x when it is less than 0.1, and also determine the linearity of the output voltage with respect to x when x is large. So, this is a part B of the problem, and part C is that what happens to the linearity and sensitivity when the following circuits is used instead of using the Wheatstone bridge signal conditioning circuit. So, instead of Wheatstone bridge signal conditioning circuits, we will use one op-amp based circuits, and we will consider the linearity, sensitivity, all these things in details. We will find there are some advantages of using the op-amp based circuits. So, we will discuss that things in details. So, let us look at the circuit. This is the circuit, right. So, our solution starts here. See the solution of problem A. You see, we have the bridge, which looks like this. This we have excitation to the bridge, and we are taking the output voltage. So, this is the output voltage EO. So, this is the resistance R, this is 2R, this is R, and this is our RTD. So, its resistance is 2R multiplied by 1 plus X, right. Now, solution looks like this. Now, you see in this particular case EA is equal to 2 by 3 of EX, EB. So, if I take this terminal A, this as B. So, EB equal to, I can write 2 1 plus X upon 3 plus 2X EX. Therefore, the output voltage EO will be equal to 2 by 3 minus 2 1 plus X upon 3 plus 2X multiplied by the excitation EX, right. So, I can write here that output voltage by the excitation will be given by 1 by 3 6 plus 4x minus 6 minus 6x upon 3 plus 2x 3 plus 2x. So, which will give you, let me take a new page, that E naught by E x equal to minus 2x upon 3 plus 2x. So, this is equal to 2 by 3 x upon 3 1 plus 2 by 3 x, right. Now, when x is small, this mod of this, if I take, that means mod of output voltage by the excitation equal to 2 by 9, these will be all small. So, I can write 2 by 9. So, this will be neglected compared to this. So, this will be only 3 in the denominator. So, 2 by 9 into x. So, obviously, if I take a new page, sensitivity I can write here in this particular Wheatstone bridge is E naught by E x upon x equal to 2 by 9, right, with some approximation obviously. Fine. Now, let us look at when x is large. Solution B, if I take a new page, when x is large, when x is large, E naught upon E x will be equal to minus 2 by 9 x upon 1 plus 2 by 3 x. So, this will be equal to k x I write upon 1 plus 2 by 3 x, right, where k is equal to minus 2 by 9. Now, let us put, for an example, let us put x equal to 1, right, which is large compared to x less than 0.1, right. So, this is usually we have taken x equal to 1, that means x is quite large compared to x less than 0.1. So, we will get the expression excuse me, we will get E naught by E x equal to 3 by by 5 into k. So, this is basically a straight line passing through the origin 0 0 and the point 2 by 3 k and 1. In actually the, if I plot E naught by E x in the y axis and x in the x axis, right. So, this will have a locus which will look like, if I take a new page, that E naught by E x will be equal to 3 by 5 k x, right, which I can write again E naught equal to 3 by 5 k 1 into x, where I can write k 1 is equal to k E x and it is a constant, right. But the actual value of the output voltage, actual value of the output voltage is, if I take that one as E naught dash equal to k1 x, okay, the very first equations, 1 plus 2 by 3. This is a generalized equation, is not it? Because that is the actual value. We have approximated in some cases, says k x less than 0.1, x less than greater than, I mean equal to 1, like all this. The error voltage obviously will come up as the error voltage so I give it name delta E naught equal to k1 x 3 by 5 minus 3 by 3 plus 2x equal to 3 k1x by 5. So, it is 3 plus 2x minus 5, 3 plus 2x. So, it is coming 3 k1x by 5 multiplied by 2x minus 2 upon 3 plus 2x, right. Now, let us take a new page. Now, to see the errors, to see whether the error is maximum with respect to x, we differentiate delta E naught, right. So, we differentiate with respect to E naught, delta E naught with respect to x. So, we will get d of dx 3 k1 by 5 2 x square minus 2x by 3 plus 2x, right. So, this I will give you the value 3 k1 by 5 del of del x minus 2.5 plus 7.5 upon 3 plus 2x, right. So, del of delta E naught by del x will become 3 k1 by 5 1 minus 15 3 plus 2x whole square. Now, that is, therefore, for maximum value of delta E naught, we will get 3 plus 2x whole square equal to 15. If I take a new page, that means x is equal to root 15 minus 3 by 2, which is equal to 0.436, right. Right. Yes. So, delta E naught max equal to 3 k1 by 5 2 into 0.436 minus 2 upon 3 plus 0.436 equal to minus 0.127 into 3 k1 by 5, right. Now, linearity will define. So, the percentage linearity is defined as, I should say percentage linearity equal to maximum drift shift divided by full scale deflection into 100. So, we will get the linearity. So, the percentage linearity in this case, is equal to minus 0.127 3K1 by 5 by 3K1 by 5 into 100. So, this is coming as minus 12.7%. So, this is the answer, right. Now, let us solve the third C. In C, we are saying that instead of Wheatstone bridge, we are connecting one op amp. The circuits already we have shown. So, for that circuit, how the sensitivity will change or the linearity will change. Let us look at that. Okay, let us take a blank page again. So, this is a solution to the problem 17.1 C. So, problem solution. Now, let us read out the circuit again. The circuit looks like this. Is op amp here. R, this is A point and this is all the 4 resistors are as usual as before, but we have taken 1 plus X, right. So, this is our RTD. This is our RTD. So, this is 2R. Now, we are connecting excitation and taking the output from this terminal, right. So, voltage at the point A, which if I defined as EA, will be equal to 2 by 3 of excitation, is not it. Now, if I apply the KCL, at node A, I will get Ex minus Ea by R equal to Ea minus E naught by 2R 1 plus X, or quite obviously it will be, if I take a new page, I will write again Ex minus 2 by 3 excitation equal to 2 by 3 Ex minus E naught upon 2 1 plus X, or 1 by 3 Ex minus equal to 1 by 3 Ex 1 plus X half of E naught 1 plus X, or I can, if I take 1 by 3 X common, so it will be 1 upon 1 plus X equal to half of E naught upon 1 plus X, right. So, this will lead to an expression E naught by Ex equal to minus 2 by 3 X, right. If I take the mod, so it will look like, if I take a new page, so if I take mod of this Ex excitation equal to 2 by 3 x, right. So, sensitivity in this case I can write that E naught upon Ex by x equal to 2 by 3. We have seen that the sensitivity has been improved in this case, and also it is perfectly linear. That is most important. In first case it is we have the final output also becomes very much linear. So, this is the improvement over the previous case, right. So, now let us go to the problem number 2, 17.2. So, if I problem number 17.2 is telling that resistance temperature detector RTD, this is also an RTD, a resistance temperature detector is required to measure the temperature correctly in the temperature range of 75 degree centigrade and 125 degree centigrade with the resolution of 0.5 degree centigrade, right. This is the range. I will not measure below 75. This is very common in industrial problem, that is we are not always necessarily will measure from 0 degree centigrade to 30 degrees. So, there is a particular range. So, within that range what will be my signal conditioning circuitry, that we will look at. So, it is 75 degree centigrade and 125 degree centigrade with a resolution of 0.5 degree centigrade. Design a signal conditioning circuits for the above, for these above requirements, and some data are given. So, they are that alpha, that is temperature coefficient of resistance of RTD, is 0.002 per degree centigrade, and resistance of RTD is 350 ohm at 25 degree centigrade, and PD power dissipation factors we are using 30 milliwatt per degree centigrade, right. So, this is the problem. Now, let us look at the solution, right. So, let me take a blank page. See, the signal conditioning circuit should give a 0 volt at 75 degree centigrade and 5 volt at 125 degree centigrade. That means, we define our output range is 0 to 5 volt, 0 to 5 volt, right. And we need this, you see, basically one Wheatstone bridge along with the instrumentation amplifier. The Wheatstone bridge is necessary to give an output of 0 volt at 75 degree centigrade, and the output of the Wheatstone bridge will be very small, and hence an instrumentation amplifier is necessary. Now, we have proposed the following circuits, right. Let us look at the circuit. Let us look at the circuit. The circuit looks like this. Let me take a blank page again. So, I have a instrumentation amplifier here, and this resistance we have taken variable. So, this RTD is connected here. Here we have this excitation, this is Ex, okay. So, this is our RTD, this is R2 and this is R1, this is also R1, this is our RTD sensor, right. Now, instrumentation amplifier is necessary because the output voltage is very small, right. So, this is our EA, I should rather name it EA, this is our output, and this is the instrumentation instrumentation amplifier, right. So, a variable resistance R2 is necessary, so that the bridge remains balanced at 75 degree centigrade. We take that Ex equal to suppose 10 volt, right. Let us take a blank page again. So, if it is there, so you see now resistance of the our RTD will look like this. RTO, resistance of the RTD, at 25 degree centigrade. RT is the resistance of the RTD and it at temperature of T degree centigrade. RTD at T degree centigrade, and RT obviously we know is RTO at 0 degree centigrade plus alpha. We taken the first order approximation, so it will look like this. So, quite obviously that means RT at T equal to 75 degree centigrade will be 350, it is already given 350, right, it is given, multiplied by 1 plus 0.002 into 50. So, this will give you 385 ohm, right. Now, to keep the bridge balanced at 75 degree centigrade, R2 is to be adjusted to 385 ohm, right. So, in that case bridge will be balanced. Now, the question is we need a resolution of 0.5 degree centigrade, right. So, if you have a resolution of 0.5 degree centigrade, the output should change by 0.05 volt for every change of 0.5 degree centigrade in temperature. Now, the error may be introduced due to self heating of the RTD. To ensure that this is not so, we choose the temperature change due to self heating to be the 10% of the given resolutions. So, we have taken the delta T for self heating equal to 0.05 degree centigrade. Now, delta T we know equal to P by PD, right. Where P is the power dissipation in the RTD, right, in watt is the power dissipation in the RTD in watt, and PDD is the dissipation constant of RTD, it is in watt per degree centigrade, right. So, this is the all the units of now maximum allowable, we take a blank page, maximum allowable power dissipation in the RTD is equal to P equal to delta T into PD. This is the maximum allowable power dissipation in the RTD. So, this will be equal to quite obviously 0.015 watt, right, which is equal to obviously this will be equal to I square and RT, right, I square RT loss. So, I can equate this thing. So, if I write I square RT equal to 0.0015, so the resistance at 75 degree centigrade will be, as we know it is 385 ohm. So, current I which is flowing through RTD at 75 degree centigrade is equal to 0.00197 ampere or equal to almost equal to 0.002 ampere. This is the current which is flowing to the RTD. Now, from the Wheatstone bridge circuits, quite obviously I can write from the Wheatstone bridge circuit I can write I equal to RT plus R1 equal to 10 volt, quite obviously. So, this will give you that RT plus R1 equal to 5000. So, RT we already know it is 385 ohm. Therefore, R1 will be equal to 4615 ohm, right. We choose a standard value because this resistance will not be available. So, we choose some standard value. We choose a standard value of excuse me, value of 4.7 kilo ohm, right. Now, as temperature increases, the value of the resistance increases, but still that does not introduce much of error. I mean, these resistance may also increase, but it is not that temperature sensitive. Now, again from the Wheatstone-Bridge circuit, we see that, let me take a blank page, that output voltage EA equal to 385 plus X upon 5085 plus X minus 385 by 5085 into 10, right. So, X is the change in the resistance of the RTD, as X is very small compared to 5085. So, we can write approximate EA equal to 10x upon 5085, right. Now, what will be the gain of the instrumentation amplifier? Now, you see that output of the instrumentation amplifier we can write EO equal to K into EA. So, where K is the gain of the instrumentation amplifier. Now, E naught equal to 0.05 volt for 0.5 degrees centigrade change of temperature, change in temperature, and X equal to 0.35 ohm for again 0.5 degrees centigrade change in temperature. So, K equal to, we can find K equal to 72.64, right. So, the gain of the amplifier, instrumentation amplifier, should be like this. So, this completes our design of the problem number 17.2. The next problem will be on thermistor. Let us solve that problem. It's thermistor problem. It is telling that find the temperature versus output voltage relation for a thermistor using the following linearization technique. Number A, using a resistance in parallel to a thermistor, right, resistance in parallel to a thermistor, and B, using a thermistor in a Wheatstone-Bridge, right. So, this is the a thermistor with two different problems we are given. So, let us take a digital class, we will take a board, right. So, this is our problem. Now, we know that in the case of thermistor, that we all know the thermistor will have a relationship R equal to R naught exponential beta 1 by T minus 1 by T naught, right. Now, suppose T is equal to T naught plus delta T. So, we can write R equal to R naught e to the power beta 1 upon T naught plus delta T minus 1 by T naught. So, R naught e to the power minus beta delta T by T naught square. So, this I can write R naught into e to the power minus x, where x equal to beta delta t by T naught square, is not it? Let us take a new page using a parallel resistance. So, if I take a parallel resistance, so this is our thermistor R T, I am using with a parallel resistance. So, this is our thermistor symbol typical. We are assuming that in this case that parallel resistance has the same resistance as the thermistor at the temperature of the T0. So, we will get the equivalent resistance of in this case R equivalent is equal to R T R naught upon R T plus R naught equal to R naught square e to the power minus x upon R naught 1 plus e to the power minus x. Excuse me. This I can write R naught one plus e to the power x, right? Clear. So, R equivalent I can write equivalent equal to R naught 1 plus e to the power x to the power minus 1, right. So, quite obviously this I can expand and tell that So, this R equivalent becoming R naught 1 plus half minus x by 4 plus x cube by 48, write this one, right. Clear? Fine. Now, we see that x equal to beta delta t by T naught square, which is very small value. Therefore, x to the power q 48 and higher order terms become negligible. So, this becomes very negligible. Therefore, we see that more or less a linear relationship between the resistance and R equivalents and temperature change delta t, right. So, this will almost equal to 0. So, these two terms will be dominant, right, because this is very small. Therefore, we can predict that R more or less linear relationship between the resistance R equivalent and temperature change delta t, right. If you put delta t here, so it will be, that means this thing here, so it will get this. Now, part B is, again let me draw the, so it's, I put the thermistor now in the Wheatstone bridge, right, and look at linearity business. So, I have the output E naught, so I have a power supply. Now, in this scheme all the resistance are made equal to the thermistor resistance R0 at temperature T0, right. So, I assume that the R0 plus equal, all the resistance are equal, this is equal to the thermistor resistance at temperature T0. From the circuit we can write, obviously, see there we can write that E naught by Ex equal to half minus R naught e to the power minus x upon R naught 1 plus e to the power minus x, right. So, I can, if I take a blank page, E naught by E x equal to 1 plus e to the power minus x minus 2 e to the power minus x upon 1 plus minus x. So, this will give you e to the power x minus 1 and e to the power x plus 1, is not it? Because this is e to the minus x, okay, fine. Now, e to the power x minus 1, we know x plus x square by 2 plus x cube by 6 plus so on, and e to the power x plus 1 is equal to 2 plus x square by 2 14. So, I can write here that E naught by E x will become x by 2. If we make a long division, of this, it will become x by 2 minus x cube by 24 plus 1. So, we can see that the using a Wheatstone bridge also, the relation between the output voltage and the temperature change is almost linear, right. This proves this part. Now, let us go to the problem number 17.4. This is on a thermocouple, right. So, this is on a thermocouple. It is telling a K-type thermocouple is used to measure a certain temperature change range, and the signal conditioning circuitry is kept at a distance from the place of the measurements. That means, I need a cold junction compensation, because if the point of measurements and the point of the installation of the sensor and the point of the voltmeter is far away, I need some phase, compensating cable, right, or lead wire sometimes we call it. So, we know actually from the when we studied a thermocouple that for K type of thermocouple, which is basically chromolevel thermocouple, what should be the lead wires, right. Now, the question is, design a signal conditioning circuitry taking into account the noise as well as the cold junction compensation, and use a thermistor for cold junction compensation, right. So, instead of using AD590 and all these things, use a thermistor, because we have seen that by using AD590 we can make cold junction compensation, but here we are asking you that make the cold junction compensation using a thermistor, right. So, this is your problem, fine. If this is the problem, so let us look at the solution. Now, since the signal conditioning circuitry is placed at a distance from the place of measurements, we need some lead wires or compensating cables. Here we are using K type of thermocouple. So, it is a chromolevel thermocouple. So, the lead wires or compensating cables we will use is a copper constant end, right. There are two types of lead wires. So, we have chosen copper constant end here. Now, a thermocouple is an active transducer. It gives very few millivolts as the output voltage. Hence, they are highly prone to noisy environments. So, noise can also be introduced by the signal conditioning circuitry from the power line, all these things. To remove this, we may use a capacitance between the power supply and the circuit. Noise is also introduced by the capaciting coupling and the magnetic coupling, so are introduced in the circuit, right. Now, to measure this, we may use a shielded pair of twisted cables with the shield grounded. It is then passed through the low pass filter before feeding to an amplifier. Then we can see the circuit looks like this. this is the circuit. You see, this is a shielded cable, the type K thermocouple. There is a compensating. This is a shielded. This is a shield, and this is a twisted pair compensating cable, because thermocouple will end here. So after that it will go. So it is going to low pass filters. Ultimately it is feeding to the instrumentation amplifier. So we are using some capacitor. We will introduce, eliminate the power supply noises and all those things. So this is our complete circuit, right? An instrumentation amplifier with high CMRR needs to be used so that any common mode noise signal will be attenuated, right? So this is our. Now see that for cold junction compensation we use a thermistor. Fine. Thermistor being a nonlinear devices, we need to use a linearization techniques. This is then passed through an amplifier to make the sensitivities of these two circuits identical, so that it will take care of ambient temperature fluctuations or variation, right. Right. So the circuit will look like this. Let me go down. Yes. So we have cold junction compensation circuit, right. These circuits will be used along with the thermocouple circuit to some final signal conditioning circuit, so that to avoid any change in the ambient temperature. This is an amplifier. This is output voltage E2. First case output voltage is E1. We have chosen RO. This is RO. This is RO. This is RT. Now this cold junction compensation circuit, as it happened in the case of 8590, also should be placed close to the reference junction temperature, so that any fluctuations in temperature of the environment will be nullified, right. So that in that case it will sense the temperature of the cold junction actually, right. Ideally they should be within the isothermal block, and the total circuit is shown in the next slide. So let us look at. So this is our complete circuit diagram, you see, right. You can see here, this is a type K thermocouple. These already we have shown. This is a figure, the circuit 1 and circuit 2. This is E1, this is output voltage. It is not cold junction compensated. We have a reference junction. Now this we put on an isothermal block. You see here, and this is our circuit which I have used. Is not it? Just now we have used this circuit. Yes. So this is our thermistor. This is our thermocouple. I need cold junction compensation. So this is isothermal block. Then this is a, you see this output is coming down here. So any change will be obviously what will happen, it will be subtracted. So the output voltage is E naught equal to E1 minus E2. So the difference amplifier is coming, because this will give you high input impedance. This is output to the, this is coming to the instrumentation amplifier, right. So this output is coming down here. So the difference I am getting output here, right. So this way also I can make the cold junction compensation, right. Fine. So we can now come to the problem number 5 or 1755. It is telling that a simple potentiometer circuit as shown in the figure is used to measure the EMF of a iron constant and thermocouple. A fixed voltage of 1.215 volt is applied across the points A and B. A current of 3 milliampere flows through the resistors, and the range of temperature variation is from 150 degrees centigrade to 650 degrees centigrade. Find the values of R1, R2 and Rg for an ambient temperature of 25 degrees centigrade. Let us look at the circuit diagram. So this is our circuit, right. It is telling that we have to find the values of R1, R2 and Rg for an ambient temperature to 25 degrees centigrade. Okay, so these are iron constant and thermocouple, right. So the fixed voltage is 1.215 volt standard voltage, which will not vary, applied across the points A and B, right. And we have a galvanometer to know the current. Now we have given also some data. So data are EMF at 25 degree centigrade is 1.022 millivolt, EMF at 150 degree centigrade is 14.682 millivolt, and EMF at 650 degree centigrade is 53.512 millivolt, right. That is EMF at 150 degree centigrade, EMF at 650 degree centigrade 53.512 millivolt. Now let us look at the solution. Solution looks like this. Now you see the current is 3 milliampere, is not it? Sorry. Okay. Current is 3 milliampere. No, I should go to the okay. Now see what will happen here. Let me draw the circuit again, so that will be more clear. So we have R1, RG, R2. It is connected to a thermocouple. Galvanometers. So I have a point here. So this is R1, this is RG, and this is R2, this is A, this is B, right. So this is our iron constant and thermocouple. Constant and thermocouple, right. So it is have a range. So we are saying 150 degree centigrade to 650 degree centigrade, right. So the current is of 3 milliampere, is not it? This is given. So let me now make the solution. So the current is 3 milliampere. So I equal to the voltage E, okay, divided by R1 plus R2 plus RG. So I will get that R1, because this, I am sorry, so this should, you see this plus RG. Now E is given, E is equal to 1.215 volt. So R1 plus R2 plus RG equal to 405 ohm. Now the measured voltage at 150 degree centigrade is EMF at 150 degree centigrade minus EMF at 25 degree centigrade. So this will give you 13.66 millivolt. Similarly, the measured voltage at 650 degree centigrade is EMF at 650 degree centigrade minus EMF at 25 degree centigrade. So, this will give you the value 52.49 millivolt. Now, at 150 degree centigrade, from the circuit we can see that R1 into current is equal to the measured voltage at 150 degree centigrade, right? It is not very good, I should erase it. So, take the pen again, 150 degree centigrade, right. So, or I can write R1 is equal to 13.66 by 3 is equal to 4.55 ohm, right. Similarly, at 650 degree centigrade, R1 plus Rg equal to 17.496 ohm. So, Rg will become 12.95 ohm. So, R2 will become 405 ohm minus R1 plus Rg equal to 387.5 ohm. So, if I write all the answers at one point, it will be R1 equal to 4.55 ohm, R2 equal to 387.5 ohm, and Rg is equal to 12.95 ohm. So, this is our answer to the problem number 17.5. So, in this lesson we have seen that we have solved several problems on the temperature sensor. When we discuss the thermocouple, we have solved one problem, while if the compensating cables terminals change, then what will be the effect on the output. But these are we have solved several problems in this particular lessons only on the problems on the temperature sensor. This ends the lesson 17 of industrial instrumentation.